When we picture someone writing software, it's easy to imagine a solitary coder sitting in a dark room, typing out a brilliant script that executes perfectly on their local machine. But code written on a single laptop for a single purpose is rarely a finished product. It's an isolated artifact. The moment that script is exposed to the demands of a live production environment, it tends to shatter. That fragility comes from three specific forces: scale, uncertainty, and interoperability. A local script simply isn't designed to handle thousands of simultaneous users, unpredictable inputs, or the need to talk to older legacy systems. To survive those forces, we apply software engineering. It is the application of a systematic, disciplined, and quantifiable framework to turn fragile code into a resilient system. Writing a quick script is essentially an exercise in typing. Building something that survives the real world requires constructing an entire engineered ecosystem. The first breaking point for any piece of software occurs the second it leaves the hands of its creator and falls into the hands of an actual user. As computing moved out of the lab and into the hands of the general public, a massive knowledge gap emerged. A person studying a manual on a home PC doesn't share the programmer's technical background or understand the original intent of the code. Users click the wrong buttons, enter letters where numbers should go, and push systems in unanticipated ways. Undocumented and untested code crashes almost immediately under this pressure. This brings us to a core rule in the field, often cited as Pressman's fourth principle: what you produce, others will consume. Because the audience is potentially massive, developers have to anticipate human error through rigorous usability design, extensive unit testing, and clear documentation. Crossing this threshold requires wrapping the raw code in a layer of protection. The personal tool evolves into a robust programming product, capable of withstanding human unpredictability. Protecting code from users is only half the battle. The second breaking point happens when a program is forced to share resources and communicate with external hardware or independent pieces of software. With the rise of massive mainframes in the 1960s, computing environments became heavily interconnected. Programs could no longer run in isolation. They had to coordinate with tape drives, memory units, and other active processes simultaneously. To prevent crashes, developers rely on component-level design. By breaking a program into components, teams isolate functions and manage data flow. Each piece communicates through a strict interface. Like threads on a screw, these interfaces guarantee parts lock seamlessly. Through modularity and strict interface design, a collection of separate applications merges to become a coordinated programming system. When you combine those two achievements, making software robust enough for millions of users and modular enough to run on complex, interconnected hardware, you reach the apex of software complexity, the programming system product. Building something at this scale requires a staggering amount of human coordination. You have dozens of specialists, from database architects to user interface designers, all working on the exact same project at the exact same time. Without a structured way to manage the work, teams of this size would overwrite each other's progress and grind to a halt. Success here depends entirely on organizing what are known as the 4 Ps: people, product, process, and project. The core tool holding this massive operation together is Software Configuration Management, or SCM. It is the discipline of identifying, tracking, and controlling modifications as a program evolves. Using version control, SCM tracks every single line of code altered by every engineer. Those edits are then reviewed and merged to converge into baselines, formal checkpoints that serve as a locked, stable foundation for the next round of development. Software configuration management operates as the central nervous system of the project, ensuring that continuous updates and exponential complexity result in progress rather than a catastrophic failure. Once a major piece of software finally ships, there is a natural assumption that the work is finished. The reality is that deployment is only the beginning. In the 1970s, researcher Meir Lehman established the law of continuing change. He observed that software implemented in a real-world computing context must continually adapt to its environment, otherwise it becomes progressively less useful. This chart shows how software engineering resources are actually spent over a system's lifespan. Only a fraction of the budget goes to the initial creation, while up to 70% of all effort is dedicated entirely to maintenance and re-engineering. The initial launch of a product is exciting, but it is brief. What follows is a decades-long grind to patch bugs, adapt to new operating systems, and rewrite legacy code before it succumbs to structural decay. Software engineering is a commitment to an endless lifecycle. It is the ongoing work of keeping a highly complex, logical machine alive and adapting in a world that never stops changing.